Welcome to Brain Vision.
So this problem has us looking at the magnetic field lines that are produced by two wires coming out of the page. And so we're asked to show that these field lines will look something like this here. So that's figure 10 in the book, although that one looks a little bit nicer than this here. So we want to show it looks something like this, and we want to do that using equation 1. And so equation 1 is just B equals mu naught I over 2 pi r. So this is just the magnetic field from a single current carrying wire. So we want to apply this to this situation and then find that the field lines look something like this. So to start, we can just say that this total magnetic field at any point is just going to be the magnetic field from wire 1 plus the magnetic field from wire 2. So when we're adding two fields like this, usually the easiest way to do it is to break each one down into components, and then we can add those components and kind of reconstitute the full vector. So in order to do that, we need to kind of define our coordinate system here. So I'm just going to pick some arbitrary point over here. We'll call that point P. And so then let's see how we'd write these vectors for wire 1 and wire 2 at that point. So for wire 1, we just draw our r vector. So we have some distance r1 going there. And that'll be making some angle theta 1 with the horizontal. But so what we have to remember is that the magnetic field line itself is going to be going perpendicular to this line. So it'll be going straight up at this point. So tangent to the field lines in blue we've drawn here, and then perpendicular to vector r1. And so we have to be a little bit careful with our angle theta when we're breaking things into components. So we could extend line r1 out here, and that will be making, or rather, let's just break this line into components. So we drop down a vertical line, and then we make a right angle. And so this right angle now, this is also a right angle up here. And so basically we've just rotated. This triangle here is a similar triangle to this. It's just rotated clockwise by 90 degrees. And so if this is theta 1, then this angle in here, right in there, is also theta 1. So that just means our x and y components are going to be kind of flipped from what we're used to. So to get the x component, it looks like we would now be taking sine, so opposite over hypotenuse, to get this little part of the triangle. And then the y component would be cosine, adjacent, to get this point over hypotenuse. So rather than the normal cosine being x and sine being y, we have that flipped in here. And looking at wire 2, there's my not as cleanly drawn line R2, but we have the exact same situation. So we'll call this theta 2. And by the same reasoning, we're going to find that the x component of this is going to be sine of theta 2, and the y component will be cosine. And now we can go ahead and start writing B1 and B2. So we'll say B net should just be, so we'll start by writing B1. I'm going to preemptively then factor out this mu naught over 2 pi r. So mu naught times I over 2 pi r1. And so this is now, originally this is a vector, and now this is just the magnitude of r1. And now we're writing the components in here. So one thing we want to note also is the signs, the plus and minuses that we'll have here. So theta 1 right now is a negative angle. So that would tell us that the x component would be in the negative direction if we just took sine of theta. But it looks like it's actually in the positive direction here. We can see this is pointing outwards a little bit. It's easy to see if we look at a point over here maybe. So there, theta is negative, and yet the x component at this point is definitely in the positive direction. So it looks like we actually need to do negative sine of theta 1. So that's just kind of based on how we've set up our coordinate system here. So we have negative sine of theta 1, and that's in the x or the I hat direction. And then we'll have plus cosine of theta 1 for the j hat component. So that one looks like it works out okay when we have an angle that's in the right half over here. So over on this side, we'll get a positive value. And that looks like what we want here. That's when the lines are going upwards in the y direction. So we have that is for our first wire. And then we'll have basically an identical term for wire 2. So mu naught I over 2 pi r2. And now we have negative sine of theta 2 in the I hat direction and plus cosine of theta 2 in the j hat direction. So now we usually want to group these by component. So we'll just kind of factor and rewrite things. So we have the I hats and the j hats together. And when we do that, we should get something like mu naught I over 2 pi. So we can factor that whole thing out. And then we'll have negative sine of theta 1. And now this is divided by r1, so the part from wire 1. And then minus sine of theta 2 over r2. So these are all the I hat components. And then we'll have our cosine terms. So cos of theta 2 over r1, cos of theta 1 over r1 plus cos of theta 2 over r2. And that is in the j hat direction. So right now this is our full equations. This is really all we need. This fully describes what the field should be at any given point. So that point is defined by a distance r1 from wire 1 and a distance r2 from wire 2, and then the angles they make. So we could plot this and we would find a vector field that looks something like this. But that could be a little hard, and probably just looking at this, we can kind of see that this shape at least seems like it's basically right. So to start, if we imagine that we're close to one wire, so let's say that we're looking at points very close to wire 1. Well, R2 is going to be big then, and so all of the contributions from wire 2 are going to end up being very small because they're divided by R2. And so it'll be divided by a large number, make a very small contribution. R1, on the other hand, will be very small, and so give us a very big value. So when we're close to one of the other wires, it's probably pretty fair to kind of say we're only really dealing with that wire. And so then we just get these circular field lines, as we'd expect in that case. And this must be true if we imagine these distances being very, very far apart. Obviously, if these are millions of miles away, R2 is not going to be having a big effect on this first one. So as for these kind of other shapes when we're more in the middle between the two, well, let's look at a line that's exactly equidistant between the two. So this line, R1, anything on here will be exactly the same distance from wire 1 and wire 2. So R1 and R2 are always equal when we're on this line. And so now let's just pick some arbitrary points over here, point P, and we can kind of start to see what these field lines will be doing. Well, if we think about the x component, now our R1 looks something like this. And so we're making a very large angle. So it looks like we're going to be in the third quadrant. And we can see then that when we take cosine of that for the x component, we should have something that's negative, right? So cosine of this angle is going to give us a negative value. Whereas for R2, we have cosine of something that looks like it is between 0 and 180 degrees. And so at this point here, that should be giving us a positive value. And so when we plug in, then we have minus of a negative term and then minus a plus term. So we have plus minus a plus, and we're going to end up with 0 since the r's are equal here. So we get no I hat term anywhere along this line, which seems like it's lining up. And then if we look at the y component, we're going to have a cosine here of this angle. So for this large angle, that'll give us a negative value, and then cosine for this one will give us a positive value, also a negative value, since that's greater than 90 degrees. And so then we just get a negative plus a negative, so something that's pointing downwards, as we found our field lines were doing. So that at least seems like it's plausibly making sense in the middle. Along this line, we should have no x components. Things are going downwards in this quadrant. Over in this quadrant, we find that things are going upwards in the y direction. So basically, we have these two lines, two field lines from these two wires that are basically independent of each other when they're close to the wire. And when they get close, they kind of merge. And along this point, we only have the y components acting. So then we're asked to look at the field lines, or rather the potential lines, lines of equipotential from 2-point charges. And so I won't draw that because it's going to look identical to this. So if we replace these two wires with just two positive charges and drew lines of equal potential, it would look exactly the same as this. And that's because the potential from a point charge is just 1 over 4 pi epsilon naught times the charge over the distance. So a bunch of constants and then times 1 over r, which is just like what we have here, a bunch of constants times 1 over r. So when we add up these potentials from 2-point charges, we'll get something that looks exactly the same. So if there are a few important differences though, and so when we're drawing our magnetic field, this is a vector field, and so we're showing direction. So we're drawing arrows here showing the direction that the vector is pointing, but we aren't saying anything about the magnitude. So there's no way of indicating that the field is stronger closer to one of these wires than farther away. So we show direction but not magnitude, whereas when we draw these equipotential lines, we can only show magnitude, and in fact, potential is just a scalar. So all we show are lines that have the same value, but there's no indication of direction. So the only difference in drawing these would be we would no longer have these arrows, and now these lines would be places of constant potential rather than directional lines.